Good evening, everyone. Thank you so much for joining us tonight. My name is Catherine McBride. I'm the director of MacIver's Grant Public Library here in Dyersburg, Tennessee, and I have the very good fortune to introduce our special speaker for tonight's event. Before I tell you a little bit about Dr. Rupke, I do want to encourage you to be posting your questions right here inside of our Facebook page during the event as we keep going. I'm going to be keeping an eye on that, and I'll be asking those questions as you post them of Dr. Rupke. And of course, how often do you get to have your burning questions answered by a physicist? If you're anything like me, of course, the response is never. So I'm very excited to introduce to you Dr. David Rupke. He is an associate professor of physics at Rhodes College here in Memphis. His teaching focuses on astronomy, astrophysics, quantum physics, and his scholarship explores the nature of galactic winds, black holes, galaxy formations. Dr. Rupke is also going to be touching a little bit on the importance of NASA's James Webb Telescope. This is scheduled to launch in mid-December, and we've been celebrating it here this past month at the library. So this is going to be absolutely fascinating. So as soon as questions occur to you, be sure to post them. So without any further ado, I'm going to bring on Dr. Rupke.
Thanks, Ms. McBride. Thanks for that lovely introduction and for raising everyone's expectations.
I try.
Hopefully, I won't dash them. Yeah, I'm here in my Memphis home, but happy to be talking to folks in Dyersburg and maybe folks elsewhere as well. And yeah, I appreciate this invitation. This came about. I'm involved with some science projects related to the James Webb Space Telescope. And I signed up with NASA to be a subject matter expert on this stuff. And the idea was to connect with local folks who want to learn more about that. And so that's why I'm here with you today. I'm going to just tell you a little bit about sort of why I think the James Webb Space Telescope is going to be really interesting for science. So I'm a scientist. The James Webb Space Telescope is an amazing project an amazing feat of engineering. And there's countless folks who have been involved in building it, designing and building and testing and doing everything that is needed to get it launched. And then once it's launched, then folks like me can use it to do some cool science. So that's kind of what I'm going to focus on. And I've got some slides I'm going to share with you. So I'm going to go ahead and bring those up and talk about some of that science. So let's see. Do this here. Here we go. Okay. So this is an image of the James Webb Space Telescope on the left. And you can read all about JWST, or as the folks in my community call it. I know Webb is maybe rolls off the tongue a little easier, kind of like the Hubble Space Telescope we call Hubble. But I'm still stuck with JWST. So this is an image on the left of the telescope, and again, you can read all about it online. There's a lot of cool stuff a lot of cool images and interesting stuff about launch. I actually pulled this image on the right today, this afternoon, from the website that you can see here at the bottom of the screen, and this is the countdown for launch. So the telescope was just delivered to the island from which it will be launched, and it left some time ago. Apparently, there was some secrecy around the transportation because they were worried about pirates. Yeah, go figure. But now the countdown is on, and it seems like everything is ready to go once they get everything together.
That's so exciting.
Yeah, no, I mean, astronomers have been talking about this for so long that it's kind of amazing to actually see it, to see a countdown. It's pretty exciting. So this is Webb, and again, there's a lot of a lot of cool stuff around the telescope itself, but I want to focus on the science because that's kind of my expertise, and that's why we built the telescope to begin with. And I want to focus on a few things. One is the first reason that we designed and built a telescope like Webb, or JWST. And that's the fact that the universe is expanding, and that has consequences that make a telescope like Webb worthwhile. About 100 years ago, we discovered that the universe was expanding, or is expanding. And the main way that we discovered this is by looking at something called the redshift of galaxies. So I'm showing you in this image a spectrum. A spectrum is when you take light and you spread it out into its constituent colors. So if you look at sunlight through a prism, that's a spectrum. And I'm a spectroscopist, so I look at the spectra of galaxies. And one of the most prominent thing we see in the spectrum of galaxies is emission lines from hydrogen gas. 70% of the universe is hydrogen gas. And galaxies have a lot of it. And at particular colors, and these purple colors here in green and red in the optical part of the visible light part of the electromagnetic spectrum, we see these lines at particular colors, particular wavelengths. When things are moving away from us, such as galaxies, those lines get shifted to the red part of the spectrum. So this is called a redshift. This is similar to the Doppler shift. So you experience the Doppler shift if you're, if there's something, a loud siren, you're passing a police car or a fire truck or a train that's coming toward you. We've got lots of trains rolling through Memphis that like to blare their horns. And what you'll find is that as whatever the thing that's emitting the noise is coming towards you and then moving away from you, the pitch of that sound will be slightly different. That's called the Doppler shift. The Doppler shift for galaxies is similar. And so as galaxies are rushing away from us, their light gets shifted to the red part of the visible spectrum. So we discovered about 100 years ago that galaxies did this. And a guy named Edwin Hubble came along, and he said, okay, let's look at those Doppler shifts, and you could translate that Doppler shift into the speed or the velocity with which those galaxies are moving. So this is a graph. Scientists love graphs. And on the vertical axis here is, you read the words say recession velocity. And this is a good example of scientists making mistakes. So this is a famous paper, but he got the units of the numbers wrong. So this is actually 500 kilometers per second and 1,000 kilometers per second. So these galaxies, these are all very nearby galaxies, but they're rushing away from us at very high speeds. On the horizontal axis is the distance to these galaxies. And these distances are listed in millions of parsecs. A parsec is about 4 light years. A light year is the distance light can travel in a year. So the nearest star is about a parsec away. So 1 million parsecs is a long ways. So these are all galaxies that are located at distances of several million parsecs. It turns out he got the distances just a little wrong. This was 100 years ago, and he was one of the first people to measure distances to galaxies. So we see that the distance, the more distant the galaxies are, the faster they're moving. The faster away they're moving from us. So this was evidence for the expansion of the universe. Why is that? Well, let's take a model universe and imagine that all of the galaxies in the universe are on the surface of a balloon. So we're kind of coming out of our 3-dimensional space and going on to 2 dimensions on the surface of a balloon. But a balloon is something you can imagine, and many of us have blown up balloons. So here we have a balloon that's getting bigger, and on this balloon we've drawn some galaxies here. And I've labeled a couple of these galaxies as A and B. So Hubble's law says that galaxies that are further away are moving faster. So as the universe expands, you can see that A gets further away from this galaxy circled in red. B also gets further away from the galaxy circled in red. So as we blow up our balloon, imagine those galaxies getting further away from each other. You could try this at home by drawing lines on a balloon and blowing it up. Now, both A and B move away, but B is moving faster away. So they recede proportionally by the same amount, but in absolute terms, B is moving away much faster than A. Okay, and this is Hubble's law. So kind of coming back to this plot again, Hubble drew a line through these points, and he said that this velocity is proportional to the distance. And if you've taken algebra in high school, maybe you have, maybe you haven't. But for those of you who have, maybe remembering kind of how that works is that as one thing increases, the other thing increases. And then there's a proportionality constant between those called the slope. And the slope of this line is something called the Hubble constant. And this is a fundamental parameter of our universe. And it determines the expansion rate at any point in the universe's history. At the present day, the Hubble constant is about 70 kilometers per second per megaparsec. So it's some number. But essentially, the bigger that number is, the faster the universe is expanding. And
can I ask a question real quick?
Yeah.
And I'm sorry, you might be getting a little bit of feedback from me. So for those watching right now, I already have gone ahead and told Dr. Rupke I have no background in physics, but I've been listening to a lot of folks talk about the relativity and the existence of space-time, how that interacts with our ideas about gravity, etc. So I'm wondering, is there any kind of connection between what you're discussing right now, this constant expansion of the universe, and gravitational waves that we are experiencing as these different astronomical phenomena are going through their lifespans? And is that affecting expansion?
So indirectly. So gravitational waves are a real thing that we've just recently detected. And in fact, the folks who detected these gravitational waves won a Nobel Prize for it just a few years ago. So this is a really important discovery. And it was a prediction, however, that's 100 years old. And the prediction was based on one of the major theories in physics of the 20th century, which is called general relativity. So general relativity was the creation of Albert Einstein. And this is a way of thinking about the universe where we can we've all experienced gravity, and physicists have historically talked about gravity as a force, but it turns out we can think of gravity as changes in the shape of space and time. And so this theory of general relativity is the basis for our understanding of the expansion of the universe. So the things that I'm showing you now are the experimental evidence that the universe is expanding. So the observers measure these things. But the theory behind that the physical model is based on Einstein's general theory of relativity, which also makes the prediction that gravitational waves should exist. Now, there are things in the universe's evolution that may also cause gravitational waves that we can detect, but it's not sort of a. So yeah, I'll just leave it at that.
Okay, thank you for letting me derail.
Yeah, no problem. That's a good question. Yeah, I mean, there's a lot we could say about the expansion of the universe, but part of the reason I bring it up again is because of this redshift. And so one of the jobs of the James Webb Space Telescope is to see the most distant things that we can see. And this is an image that I love to, it's one of my favorite images, and I love to show my students and other folks I talk to. This is something called the Hubble Deep Field, or now the current version of we have of it is called the Hubble Ultra Deep Field. And actually, starting back in the late 90s, the Hubble Space Telescope stared at a very small piece of the sky. Just if you held up the tip of a pencil, at arm's length, that little piece of the sky that's the tip of the pencil is what you're looking at. And it stared at this for 10 days. Now, cumulatively, I think, they've improved on it over the years, and now it's been stared at for something like 50 days. But essentially, the point here is to if you think of telescopes as light buckets, the longer they sit there collecting light, the better they can see things that are far away. And so the goal here was to see the most distant things that we can see. So what you're seeing here, everything that you see in this image, except for a few things, is galaxies. And you can probably guess that the biggest things that you're seeing are the most nearby galaxies. And actually, the most distant things that you can see in this image aren't even visible in this representation. So they're just tiny little faint points scattered throughout this image. There's actually tens of thousands of galaxies in this image. So if you zoom in, if you grab a full resolution version of this and really zoom in, you would be amazed at all the little dots that you see.
Wow.
So why is that? How does that work? Well, the things that we're seeing that are further away are actually, why is this important for astronomers? Why do we want to see things that are further away? Well, it turns out that the things that are further away are telling us what the universe was like earlier in its history. So light, this was another discovery of Albert Einstein, is that light has a speed limit. So light travels at a finite speed, and that's actually nothing in the universe can travel faster than that. So all of the light from those distant galaxies takes a long time to get to us. So the further away something is, we're seeing it as it was longer ago in time. So the sun, light takes 8 minutes to get to us from the sun. So we're actually seeing the sun as it was 8 minutes ago. The nearest star is 4 light years away. So when we see the nearest star, we're seeing it as it was 4 years ago. The nearest galaxy is 2.5 million light years away. So we're seeing it as it was 2.5 million years ago. The most distant galaxies are, that we can see in this image are 13 billion light years away. So we're seeing them as they were 13 billion years ago. So you can imagine that this image basically gives us snapshots of the universe at different times in its history. So it's like if you have a wall, at your home where you show, if you have kids, you might show pictures of your kids at different times in their life. And, you've got the baby, you've got the toddler, the middle schooler, the angsty adolescent, the ambitious college student, et cetera, right? Mm-hmm. So that's what we're seeing here, but all in one image. The things that are most distant, so kind of circling back to that first point I made, the things that are most distant are redder. So to best see those things, we want to look at wavelengths or colors of light that are redder. And in fact, so far that we get outside of the visible light spectrum and move into the infrared part of the spectrum. So this is basically a simulation of what the James Webb Telescope might be able to do. And this is a false color image, so it doesn't really show you, sort of that infrared versus visible distinction. But another thing that's cool about James Webb is that it's much bigger than Hubble, so it can be a much bigger light bucket. So it's going to see things that are further away for that reason, but also things that are further away because it's designed to look in this infrared part of the spectrum. So this is something actually that plays into a lot of things. So many objects actually emit in the infrared part of the spectrum. If you take an infrared camera and take a picture of a person, you'll find that they are actually glowing in infrared light. And so in visible light, we see things because those things reflect visible light. But in the infrared, humans and anything that has a well-defined temperature actually emits their own light via something called black body radiation. Okay, and so when we look in the infrared part of the spectrum, we can see distant galaxies, but we can also see things that emit in the infrared part of the spectrum. So again, James Webb, just to kind of recap here, James Webb is designed to look in this infrared part of the spectrum. So I'll just stop there. I'm going to move on to talk about something related to this, but maybe I'll just stop and ask if there are any questions before I go on.
Yes, absolutely. So we have a question online.
Sure.
I have got a question as well that I've come up with. So,
Okay.
but first, let me post our Facebook question. So we've got someone who's asking, how do you think the world began, the universe began? They suggest evolution, Big Bang, creation. I'm going to even throw in some kind of combination of all of those. I'm sure you get asked that question often by your students when they first
Sure.
come into class.
Sure. Yeah. I think this is a good question because it kind of gets at the distinction. What I, as a scientist, think of the distinction between what science can tell us about the universe and what other ways of knowing can tell us about the universe. So science is really good at making models, physical models of how the universe works, and this includes a couple of theories that talk about the origin of the universe, or talk about the early parts of the universe's history. And this is called the Big Bang theory. And so when scientists say theory, they actually mean something that's really well documented and well understood and has a firm scientific footing. It's not the way that we use theory colloquially. So we might say, oh, I've got a theory about that. So when scientists say they have a theory, that means we really understand this thing. So our Big Bang theory actually is a well-established and understood theory for the very early parts of the universe's history. Now, the Big Bang theory doesn't tell us where the universe came from, why there's something rather than nothing. But we have really good physical models of how sort of those early parts of the universe's history progressed. And again, that's called the Big Bang theory. And maybe I'll leave it at that. I think that's a good answer to that question.
Yeah. And of course, I'm hoping that later on in the discussion, we'll get into your interests and passions about all those unanswered questions that are still left in the field and make the field so exciting and intriguing.
Sure.
I've got another Facebook question that also just posted while we were talking, and this one sounds fantastic as well. So the question is, are all of the galaxies different or very similar when viewed?
So I study galaxies, and this is part of why I like studying galaxies, is because there's such a diversity of galaxies. And in many ways, galaxies are a little like biological, or a little like life on Earth, in that they're complex and hard to understand, and again, very diverse. And they're always changing throughout the life of the universe. And actually, astronomers use the term evolution in a different way than biologists do. But we use the term galaxy evolution to describe how galaxies are changing over the course of the universe's history. That said, scientists are always looking for patterns, right? And so one way we study galaxies is to look for how galaxies are different, but also how they're similar, and what sort of patterns we can observe, and then how we can explain those patterns using physics and other scientific models.
And you reminded me too. I think I always thought it was so interesting the way physicists and astronomers discuss galaxies and other sort of cosmological bodies in terms of lifespan. Just like you had said, we talk about young stars and old stars and dying stars, as though they have lives, and which they do, as you said. That is all the questions we've got for now. So if you'd like to go ahead and move on
Sure.
to the next section.
Yeah, sure. So another reason why we want to look in the infrared part of the spectrum with the James Webb Space Telescope relates to what I was just talking about with the fact that anything that has a temperature emits in the black body part of the spectrum. So you all live in Dyersburg. In Memphis, the night sky is very bright. So when I walk out of my house, I can't really see the Milky Way. But I don't know if that's the case in Dyersburg or not, but
you absolutely can in some parts, yeah.
Yeah. So I mean, you guys are, I would say it's much more rural there. I like to go camping with my family, and that's when I get to see the Milky Way. Mm-hmm. And so you look up and you can see the stretch of stars in the Milky Way. This is something that Galileo, people have looked at throughout history, but Galileo, when he pointed his telescope at the Milky Way, he saw that those bright patches were full of stars. So he realized that there were many more stars in the universe than we could just see with the naked eye. It turns out, though, that we actually can't see most of the light of the Milky Way. And the reason for that is that the light is blocked by something called dust. I mean, you know what dust is, right? In your house, you spend your life trying to clean up dust, right? Or at least we do at my house. But it turns out that there's something in space that astronomers call dust. Now, it's different from the dust that sits around your house, but it's similar in the sense that it's little bits of things, right? Little bits of material. These are two images of the sky, and what's prominent in these images are the Milky Way. And so in the lower right is an optical or visible light image of the sky. And you can see the band of the Milky Way there, but here you can really see those dark patches that weave through the Milky Way. And actually, in a really dark site, you can see the dark patches in the Milky Way as well. So that's dust. And in fact, the indigenous people of Australia actually had named some of these patches of light. So there's one that's called the Coalsack Nebula that we call the Coalsack Nebula. They call the emu in the sky. So these, if you live in dark places and spend a lot of time looking at that, you can really see this dust. Now, if we look in the infrared part of the spectrum, we can see through that dust. So the dust blocks visible light, blocks ultraviolet light, but it does not block infrared light. So there's a lot of things that we can see that we can't see in the visible light with Hubble. This includes places where stars are forming, places where planets are forming, black holes at the centers of galaxies, and I'll talk about that again in a minute. So the ability to see through that dust is really powerful. This, an example, just to show you some more detailed images. This is an image of part of the Orion Nebula. So the Orion Nebula is actually a glowing cloud of gas that looks like a star in the night sky, and it's in the sword belt of Orion. So Orion has a belt, and it has a sword belt, sword, what would you call that, sheath or scabbard, kind of pointing downward. And the middle glowing part of that, which looks like a star, is actually the Orion Nebula. And if you were to map the nebula, you would actually see that it covers a lot of that area of sky, but you can really see the bright part. And that bright part glows in certain wavelengths of visible light, but a lot of it is blocked. And so this, on the left here, you see this visible light image that certain wavelengths glow, but the dust is blocking a lot of that. Now we go and look in the infrared, and in fact, this was another infrared telescope that was active in this decade or in the previous decade, but a lot of its work was done in the 2000s, in the aughts, and these are images taken in infrared light, and here the dust actually glows. So not only can we see through the dust, but we can also see the dust itself and see what the dust is doing. And that also tells us really interesting information about again, this is a star formation region, so a region where stars are actively forming, but also about places where planets are forming and places where black holes are actively accreting, actively doing their thing. And so again, this is an example of that black body emission that I was talking about. So again, humans glow in infrared light, and so does dust. So does cosmic dust. What does that dust look like? So you may be wondering. So the dust is actually made of materials that we can experience on Earth. So there's a lot of silicates. Silicon is a major component of the Earth's crust. And there's a couple of minerals, olivine and pyroxene. These are examples of silicate minerals. Sand is made of silicate. It's made of a lot of silicates. And these minerals are, again, things that you can find easily in the Earth's crust. My brother's a geologist, and I've been rock hunting with him, and we've found, we found olivine. I know he's pointed out olivine before, but I don't think I could do it. So some of it is silicates, and then a lot of it is also carbon. So again, imagine the most abundant elements on Earth: carbon, silicon. These are the things that are found in cosmic dust, and these are microscopic particles. So these are actually bits of cosmic dust: silicon carbide, graphite. Again, that's the stuff that makes up your pencil. And this is actually an image of dust from a comet. So these are microscope images, right? So very detailed images that zoom in, and these things are much, much smaller than they're comparable probably to the width of a human hair or something. So they're very, very small particles. But you collect a whole bunch of them in the universe, and they can glow in infrared light, and that's what the Webb telescope will see. Talked about dust. Talked about why we want to look in infrared with the James Webb Space Telescope. One is because we can see things that are further away more easily. Another is that we can see through dust, and we can see dust. And then I'm going to talk. Now I want to talk finally about the particular science that I'm interested in. But before I do that, maybe I'll stop and just ask if anybody has any questions about cosmic dust.
Well, just to double check too, we do have a question online. So these images here that we are looking at, are these taken from the Hubble telescope, or are these elements that we have found on Earth? Were they collected off Earth?
Sure, good question. So kind of going back a little bit, let me go back here actually. I think the only image I've shown so far that's taken by Hubble is this one. Okay. Astronomers use, umpteen different telescopes. Hubble is one of the most photogenic. It produces some of the most photogenic images. I mean, it's a revolutionary telescope. And, I think one of its lasting legacies is how much it has shown everyone sort of the amazing things that are in the universe. These are actually, so we've been looking at things that are really huge, right? Galaxies, nebulae. These are actually tiny microscopic particles. And so these were actually, we've actually sent some missions that have collected some dust from space and brought them back. And we can also, I think that they can sometimes collect this stuff by having a plane go through the upper atmosphere. There's different ways to collect sort of this cosmic dust, so that we can look at it through an actual microscope. So kind of the opposite of what a telescope is doing, right? Telescope is zooming in on things that are far away but really huge. This is a microscope zooming in on things that are tiny, so you can see them better. But again, you take all of these particles and put, uncountably many together, right? And spread them through space, and then they emit this light that the telescopes can see. Well, I'll just I'll tell a little. Well, I'll just say it. I'm always a little. I always think it's a little funny talking about cosmic dust. I was in my first year in graduate school, and it was before I decided I wanted to go into astronomy. And I was joking with a friend that the university offered a course in. It was called the Interstellar Medium, which is basically a course on gas and dust in space. And we thought that was pretty funny that someone would take that course. Now that's like what I do for a living, right? But it's at
I
the
think
time
there are
it
many
seemed sort of,
people. I think a lot of folks will have very similar story talking
yeah,
about ideas that came through their mind when they were in their early 20s compared to
yes,
now.
exactly.
So
Exactly. All right. Are there any other questions before we go on?
no, not yet.
Okay. All right. So now I just want to talk just a little bit about the particular science that I'm interested in. So this is an image of a big galaxy. Actually, this is a galaxy that's at the center of the nearest cluster of galaxies to us called the Virgo cluster, which is in the constellation Virgo. And I put a little dot at the center of this galaxy, representing the massive, actually we call it supermassive black hole that's at the center of this galaxy. And this black hole is weighs about 1 billion suns, so it's very massive, but it's actually incredibly tiny. So I've drawn a dot there, but that dot actually doesn't represent the black hole. The black hole is so tiny that you couldn't represent it in this image. But I'm just putting it there so you can see that it's there at the center. So it turns out we've learned that most galaxies have a massive black hole like this at their centers, including the Milky Way. But these black holes are actually physically, so they weigh a lot, but they're physically, in terms of their size, they're very tiny. And so they're just at the centers of these galaxies. And in terms of their gravity, they only, you have to get really, really, really close. So, it only impacts gravitationally just a tiny region around it. Paradoxically, however, because they weigh so much and because you can get so close to these, because they're, in terms of size, really tiny, there's a lot of energy from gravity that you can turn into other forms of energy. So we think of black holes as being named black holes because because light cannot escape black holes, which is true. But all the stuff that gets around black holes, because it can get so close and because there's all this energy that it can tap due to gravity, that the stuff that's around the black hole gets enormously hot. And when things get really hot, they glow. So that's what I was talking about, this in the same way that we were talking earlier about dust glowing. So the stuff that's around black holes glow, but when it gets really, really hot, it gets extremely bright. So the dependence of sort of the brightness of something on its temperature is really strong. So when things get really, really hot, they get really, really bright. And so paradoxically, supermassive black holes are some of the brightest objects in the universe. So in some sense, they're cosmic lighthouses that allow us to see across the universe.
That is fascinating.
Yeah, I know, isn't it crazy?
So is that one way in which we are discovering black holes, is we're looking for perhaps temperature fluctuations out in the universe?
Well, we just look for things that are really bright.
Wow.
Which may seem strange. And in fact, we look for things that are really bright but look like stars. So the black holes are so bright that they outshine their host galaxies, and so they look like stars. So an example here, this is actually the nearest quasar or quasi-stellar object. So this is a term meaning a really bright black hole at the center of a galaxy. And it was originally called a quasi-stellar object because people looked at it and they took an image and they said, "Oh, that's a star." But then they took a spectrum and it didn't look like a star at all. So they realized it had to be something different. So about 55 years ago now, we realized, okay, these are not stars. These are things that are very far away. So this is the nearest very bright supermassive black hole. And so this thing at the center looks like a star. It's got this sort of characteristic cross pattern. And that cross pattern is due to something the telescope is doing to it, but it's very characteristic of an image of a star. But then swirling around it is the galaxy itself. So in this case, it doesn't outshine the galaxy, but it's still really, really bright compared to the galaxy.
And we have a quick question to you. It says that these are very tiny in relation to the universe, or in relation to the galaxy that they're found in the middle of. But someone would like to know exactly how big is tiny? Like, in other words, are we at risk of getting sucked in 2 hours?
No,
that's what's coming to my mind.
Oh, that's a good question. Yeah. So I guess for context, so our galaxy, so I said the nearest star is about 4 light years away. The center of our galaxy, where the supermassive black hole in our galaxy is about 25,000 light years away. So we are really, really far. Yeah. So it's, it's a long ways away. And actually, the black hole, in terms of its gravity, only impacts sort of a few light years around it. And once you get beyond that, then you're sort of governed by the gravity of the galaxy, not by the black hole. Now, where things get interesting is when the black hole lights up, right? So the black hole at the center of our galaxy is not shining brightly. But when black holes do decide to shine brightly, then I suppose it's conceivable that could impact. That's not something I probably shouldn't say too much about that, because I don't know much about how creating supermassive black holes affect sort of habitability of planets. I don't think it's a big effect, because it turns out that light tends to point out at the galaxy rather than into the galaxy itself. But it's an interesting question. Short answer, though, is you have nothing to worry about. Yeah.
That's a relief.
Yeah. Okay. So these quasars, again, are things that you can see across the universe. Because they're pouring out all these energies, they actually do affect the evolution of their host galaxies. And so that's why I'm interested in quasars. Is I'm interested in studying how the light and the energy that comes out of these regions around the black hole affects the evolution of the galaxy. And so it can affect the star formation that's occurring in the galaxy. And it might shut off star formation. And in particular, Ms. McBride mentioned that I study galactic winds. And so my kids like to joke about galactic winds. I think I was, there was they sometimes like to call them galactic toots. They think that's a better name for galactic winds. These galactic winds are basically outflows of gas, so flows of gas that come out of the galaxy, so they can impact the stuff in the galaxy. So I'm part of a team called Q3D, and then it has a long name here. But basically, we're working. We're going to use the James Webb Space Telescope to study three quasars that are at different points in the universe's evolution, and we're going to use a technique where we take a spectrum at each point in the galaxy, and this technique is called integral field spectroscopy, or imaging spectroscopy, as the title of our proposal says. And so basically that allows us to get a really detailed picture of what the gas and dust in the galaxy are doing. And part of our program is to develop a software package that I've been working on for about a decade now, and we're adapting that to use for the James Webb Space Telescope. So we get to be some of the first folks to use the telescope, but sort of in payment, if you want to think of it that way, we're producing this software that any scientist can then use to go and analyze their data. So another unique thing about the James Webb Space Telescope is these integral field units that it has. So Hubble doesn't have these. I can't think of a space mission that it had an integral field unit like this. And it turns out that this type of data is more complicated. I mean, you get a lot more information out of it, but it's more complicated. And so part of our goal is to help astronomers be able to use the information that comes from these new sorts of instruments that are on the James Webb Space Telescope. And our collaboration, is folks from Germany and the US and other places. And so at Rhodes, some of my undergraduate students have been involved in this project and done research in this. We've been spending the last few years working on that, and now we're really ramping up. So I'm meeting with you tonight, but yesterday we had a big meeting with folks at Space Telescope, and we have our usual collaboration meeting tomorrow morning, first thing, and so we're doing a lot of work on this, and excited to see actual data when the telescope launches.
How exciting to be at the forefront of this and creating such an important tool.
Yeah, and I should emphasize, like, we're just a little piece of like this huge array of people who are,
Sure.
and a lot of these people have been working super hard on this thing well before, I ever got involved. So there's a tremendous number of really smart and hardworking people who've been doing this. But you're right, it is fun to be able to play just a little piece, little role in that. That's all I've got in terms of my presentation, but I'd be happy to answer whatever questions folks have.
Well, I'm glad that you are throwing it back to the questions online, because we do have a great one. It's a big one, and that is, if you would just connect one more time for us the importance of black holes on and what we can learn from them on a larger scale. So I know you were talking about how galactic winds help us understand a little bit better what's going on as stars form. But again, if you would connect our research that's happening right now with black holes regarding back to why they're important on a large scale to help us with that big perspective.
Sure. Well, black holes are really interesting things, and their importance spans a really wide range of applications. Black holes were, again, another of these predictions of general relativity. In this case, the prediction wasn't made until maybe 50 years after the theory was first proposed. So the theory was first published in the 19-teens, and the existence of black holes was predicted using this theory of general relativity in the 60s. And it wasn't long thereafter when astronomers saw things and started to realize, oh, this could be a black hole. What's really cool about black holes is that we can use them to test the theory of general relativity. So this kind of goes back to what I was saying about science being really good at building models of the universe. Model building is a little like, scientific model building is a little like building Legos, in that you build a model to represent something, but scientists actually always want to break their models, because their models are never perfect representations of the universe. And the way we make progress is to find where our models are wrong. So the more we can test a theory, like general relativity, the more we can decide how much of it is correct and how much of it needs changing. So this has happened regularly throughout the history of scientific inquiry, as we make models for how the universe works, and then we realize, oh, something's wrong. Let's make a new model. My kids love playing with Legos, and something breaks, and they're kind of disappointed. But then I say, but that's the fun of Legos, right? Is you get to make a new model now, right? So the same is true of black holes. Is they're great laboratories for experimenting with general relativity and deciding how correct general relativity is. So far, it's passed with flying colors all the tests we've thrown at it, but it'll break someday, and whoever does that will might win a Nobel Prize.
Yeah, yeah.
Yeah, and so black holes are, because they're really massive, and they're places where the gravity is really strong. General relativity is really, you can explore a lot of the effects of general relativity there. So that's one reason they're important. Astrophysically, they're important because they occur not just at the centers of galaxies, and so they're really important for the evolution of understanding the evolution of galaxies. When stars die, the most massive stars, they will leave behind a black hole, a black hole that's very small compared to the ones that are the centers of galaxies, but a black hole nonetheless. And so, in the sense of why are things important astrophysically at all? Well, it's so that we can understand the universe better. And it turns out that black holes are really important components of the evolution of stars, the evolution of galaxies. And so those are a couple of reasons why it's important to study black holes.
And what I love too, I keep on going back to the images that you had of the Milky Way. I just love that we can have this conversation about such huge, abstract, wide ideas regarding, the formation of the universe. And yet you can also go outside on a country road tonight and look up and realize, yes, absolutely, that these large, abstract conversations affect us in a very real way because we are immediately part of this and experiencing this, even as these theories are being built.
No, that's absolutely true. And before I became an astronomer, I loved going outside and playing on my dad's old telescope and, looking at the moons of Jupiter or just looking at the night sky. And, I grew up in a rural area, and, still one of my favorite things is to look through a small backyard telescope at Jupiter or the moon, or, I still really find that amazing. So it's, there's stuff all around us that we can enjoy without, even without a telescope, like you said, on a country road.
Absolutely.
Dark night.
All right. Well, I think that's getting close to our time for this evening. We don't have any more questions online either. I want to say thank you so much, though, to those watching who did post their questions. Of course, to Dr. Rupke for joining us this evening. And I also obviously want to put a quick shout out to Jasenia Perez over at the Space Telescope Science Institute and those other folks who built and then put us in touch with this subject matter expert series in celebration of the James Webb Telescope that's being launched. Now, it's already been rescheduled once, unfortunately, but Dr. Rupke, you're feeling pretty confident about that mid-December launch, would you say?
Yeah, I mean, gosh, this thing was supposed to launch years and years ago, but this is an incredibly complex mission. I mean, even normal missions get delayed, and this one is not your not your average mission.
Yeah.
In terms of its complexity and sort of the technological challenges involved. So, but at this point, basically all the hoops have been jumped through, except actually just mounting it on the spacecraft. And who knows? I guess there could be some issues with that. But I get the sense that this is sort of, probably the most likely thing that'll delay it at this point will be the weather.
Well, yeah, everything in life is subject to the weather, but still to have come so far after this much time and this much work, it's just really exciting. And then, of course, soon to be getting information back. How thrilling is that? So,
yep, pretty exciting.
All right. Well, thank you again for giving us this presentation tonight, and for everyone who joined us. Again, I'm Catherine McBride. This has been Dr. David Rupke with us, and I hope everyone has a wonderful evening.
Yeah, thanks. It was a pleasure to be with you.
Thank you so much.
Yeah.